Hello and welcome. So, in our last class we have discussed the constitutive relation for a laminate. In fact, starting with classical lamination theory, we have actually established the constitutive equation for a laminate, which actually defines the characteristics of a laminate in the form of, we have developed the characteristics relation for a laminate in the form of Nm is equal to A B B D so sorry, this is K, this is the constitutive relation for a laminate which defines the characteristics of a laminate. That means, it actually relates the in plane forces and moments resultant to the mid surface strains and curvature by means of the so called ABBD matrix. Okay. We also understood the role played by each of these sub matrices. Actually, this N consists of 3 forces Nx, Ny, Nxy, M consists of Mx, My, Mxy moment resultants. Similarly, A, B and D are 3 by 3 matrices. So, we have discussed in details in the last class, and we also understood that the A matrix is actually the extensional stiffness, which relates the in plane forces to the corresponding mid surface strains, and D matrix is the bending stiffness, which relates the moment resultant to the corresponding curvatures, and the B matrix is coupling matrix, which actually couples the in plane forces to the curvature and the bending and the moment resultants to the in plane strains. That means, it couples the force resultant to the curvature and the moment resultant to the in plane strains. Okay. And we also understood in details the element of each of these matrices and the specific role each element actually signifies in terms of the behavior of the laminate. This is what we have discussed in our last class, and more importantly, we understood that each element of this ABBD matrix is actually decided by the geometrical properties and mechanical properties of the constituent lamina from which the laminate is made. When we say geometrical properties, it is the thickness of the lamina, and it is also its location with reference to the mid surface plane, or we may say the stacking sequence, how the lamina are stacked to make the laminate. So, the geometrical properties and as well as the mechanical properties of each lamina actually decides what will be the value of each of these elements, and therefore, by choosing the geometrical and mechanical properties of the constituent lamina, we can actually decide these terms. Say for example, suppose we choose the stacking sequence of the lamina and the mechanical properties such that, say, the 1/6 term is 0. What does it mean? It means we have a laminate where there is no coupling between the normal in plane normal and shear. That means, in plane normal force will lead to only normal strains and no shear strains. Okay. Similarly, suppose we choose a stacking sequence and the material properties of the constituent lamina such that all the elements of this B matrix are 0. Okay. That means, in the laminate characteristics there is no bending extension coupling. If the laminate is subjected to in plane load, it will only develop in plane stresses and no curvature, and similarly subjected to moment, it will only have curvatures and no in plane strains. So, this leads to the discussion on special cases of laminate stiffness. So, today we are going to discuss some simplification of the stiffness matrix, which leads to special cases of laminate stiffness. Okay. We are going to discuss today the special cases of laminate stiffness. Okay. How? By choosing the geometrical and mechanical properties of the constituent lamina in making a laminate, we can simplify the stiffness. How we could make some of the terms in the ABBD matrix to 0 and thereby eliminating some of the undesirable responses of the laminate. Say for example, many times we would like to get rid of this bending extension coupling, therefore, we would like to make the each element or all elements of the B matrix as 0. So, a special case of laminate. First, let us discuss symmetric laminate. Okay. So, if a laminate is made by stacking several lamina, so that for every kth layer in the laminate there exists that for every kth layer in the laminate, sorry, what about? So, we are discussing symmetric laminate. If a laminate is actually so made that for every kth layer above or below the reference plane, that is the mid surface, there exists a k private layer such that means if you have a laminate, suppose you have a laminate, n layer laminate, okay. So, suppose this is the kth layer, okay. So, this kth layer is having a distance of z k bar, which is the distance of the middle surface of the kth layer from the reference plane, okay. So, that for every kth layer above this reference plane there is a k prime layer whose distance is say z k bar k prime, okay, such that thickness of the kth layer is equal to thickness of the k prime layer, z k bar is equal to z k prime bar, and the properties, that means symmetric laminate is a laminate so constructed that for every kth layer above and below the reference plane there exists a kth layer below or above the reference plane such that T k is equal to T k prime, that means they are of the same thickness, then z k bar is equal to z k prime bar, that means they maintain the same distance from the reference plane, one is above the reference plane, other is below the reference plane, and they have the same properties, that means q bar k is equal to q bar k prime. Okay. So, this is the definition of a symmetric laminate. Basically, it maintains a symmetry with reference to the mid surface. Okay. Whatever is above the mid surface, below the mid surface is just the reflection of that. Okay. So, as a result of this, as a consequence of symmetry, what happens is B I j, each element of the coupling matrix goes to 0. We can prove that. How? We know that the definition of B matrix is okay. So, this is the definition of B matrix. Okay. Therefore, we can write this as q bar k into z k plus z k minus 1 into z k minus 1, now this divided by 2. Okay. So, this could be now written as k going from 1 to n q bar k. Okay. What is z k plus z k minus 1 divided by 2? Look at this figure. What is z k? With reference to the mid surface, if this is the kth layer, this is the reference plane, then this is z k and this is z k minus 1. Remember this what we have done during our classical lamination theory. So, and z k is the distance of the mid surface of this. Therefore, this z k plus z k minus 1 divided by 2 is nothing but z k bar. And what is z k minus 1? This is nothing but the thickness of the kth layer. So, this is T k. Okay. Now, that for every k there is a k prime for which this q bar k and T k is same, okay, and z k bar is equal to z k prime bar minus. Okay, sorry, I have not given minus here. Okay. Therefore, this since for each k there is a k bar such that z k is equal to minus z k prime, T k is equal to T k prime and q bar k is equal to q bar k prime. Therefore, B I j is equal to 0. So, this is the characteristics of a symmetric laminate. As a consequence of this symmetry, please note that this is the symmetry of geometry as well as material properties. Okay. As a consequence of that, the B matrix, each element of B matrix becomes 0. Therefore, there is no bending extension coupling. Okay. So, the characteristics is that no bending extension coupling. Okay. And simplified analysis, in the last class we have discussed the analysis of laminate, that means determination of stress and strain. Now, because it is decoupled, therefore, analysis is simplified. Also, it prevents warpage during fabrication. That means, if a laminate is made and during fabrication it is allowed to cool to room temperature from the curing temperature and it experiences the temperature gradient of delta T, if it is not symmetric, it will bend. So, that is prevented for symmetric laminate. So, the symmetric laminate could actually be maybe a symmetric cross-ply laminate. Symmetric cross-ply laminate. A symmetric cross-ply laminate is each layer is actually is a specially orthotropic layer. That means, each layer is each lamina of the laminate, each lamina of the laminate is either 0 degree or 90 degree, that is specially orthotropic. We all know what is a specially orthotropic lamina. When the material axis coincides with the analysis axis, that is specially orthotropic lamina. Okay. So, each lamina is a specially orthotropic lamina. If it is symmetric, say for example, 0, 90, 90, 0, this is a symmetric laminate. Okay. That means, I have shown a 4 layer laminate, this is 0, this is 90, this is 90, this is 0 and this is the reference plane mid surface. Okay. So, this could be written as 0, 90, symmetric. Because each layer is specially orthotropic, therefore, Q16 bar is equal to 0. Please remember what is a special orthotropic lamina. In the Q bar, that means the reduced transform stiffness matrix, the 1/6 term and 2/6 terms are not there. That means that there is no shear extension coupling in a special orthotropic lamina. And as a result of this, since we know what is A matrix, suppose A16 is nothing but Q16 into Tk for sum over all the layers. Since Q16 is 0, therefore, A16 is also 0. Similarly, A26 is also equal to 0. Therefore, similarly A26 is also equal to 0. Okay. Therefore, a symmetric cross-ply laminate, therefore, the characteristics of a symmetric cross-ply laminate, because it is symmetric, therefore, B is anyway 0 due to symmetry, and A16, A26 is 0. That means, no bending extension coupling, is absent, and no in plane shear extension coupling. Okay. Also, because Q16, Q26 is 0, going by the definition of D16, Q16K into ZK cube minus ZK minus 1 cube by 3. So, because Q16 is 0, so this is also equal to 0. Similarly, D26 is also equal to 0. Therefore, no bending, twisting coupling. Okay. So, this is the characteristics of a symmetric cross-ply laminate. Similarly, it could be a symmetric angle ply laminate. Laminate could be symmetric angle ply laminate. Okay. An angle ply laminate is actually having its adjacent plies oriented at plus theta and minus theta. This is an angle ply laminate. Okay. Adjacent lamina are plus theta and minus theta, and if the number of layers are odd, then it is a symmetric laminate. Okay. For example, plus theta, minus theta, plus theta. Okay. Say plus theta minus theta, then plus theta, again minus theta, again plus theta. So, this is a symmetric laminate, okay, having the plane of symmetry through the middle of the plus theta layer. Okay. So, this is a symmetric laminate which could be written as plus theta, minus theta, again plus theta, symmetric. For this, you can see that A16 is equal to k going from 1 to n Q16 k into T k. Okay. Now, you can see that this plus theta minus theta will cancel out, okay, and it will only remain for this plus theta. Okay. So, because since Q16 theta is equal to minus Q16 minus theta, this means that A16 for this, actually all this plus theta minus theta pairs cancel out, it remains with only Q16 theta into T k for only one layer. Okay. So, this could be written as Q16 theta into H by N. Suppose you have a laminate whose this is, suppose the thickness of the laminate is H, that is H by 2 above and below the mid surface, and each layer is T k. So, if there are n layers, therefore, T k is equal to H by n, and for large n, therefore, for large n, H by n is negligible. And therefore, A16 and A26 are negligible. Therefore, A16 and A26 could be, depending upon the, if the number of layers are large, so it could be negligible. Therefore, symmetric laminate could be symmetric cross-ply laminate, or it could be a symmetric angle ply laminate. So, next we have balanced laminate. Okay. Balanced laminate actually consists of pairs of layers with identical thickness and properties, but have plus theta and minus theta as their fiber orientation. Okay. That means, it consists of pairs of layers with identical thickness and properties, but with plus theta and minus theta as their principal material axis, or the fiber orientation, principal material axis with reference to the laminate axis, the laminate analysis axis. Okay. X y. Okay. That means, suppose with reference to this, say there could be one plus theta, then minus theta, and they in pair. Okay. That means, for every plus theta there is a minus theta layer, their thickness is same. Okay. This is a balanced laminate. Okay. So, now we know that Q16 theta is actually equal to minus Q16 minus theta. Similarly, and Q26 theta is equal to minus Q26 minus theta. How we know that? Recall your expressions for reduced transform stiffness matrix elements in terms of reduced stiffness matrix elements. That means, in the macromechanics we have studied, we could express q bar as a function of q and theta. Just go back and check that Q16 plus theta is equal to q minus of Q16 minus theta, and same is true for Q26. Okay. Since for every theta, every plus theta there is a minus theta, therefore, it implies that for a balanced laminate A16 is equal to 0, A26 equal to 0. So, this is the characteristics of a balanced laminate. Okay. So, this is the characteristics of a balanced laminate. That means, in plane shear extension coupling is eliminated. Now, what is the significance of this? Then you have to understand why we actually require angle plies. Okay. Suppose we have a specially orthotropic laminate, that means, say we have a cross-ply laminate 0 and 90, it will be strong in the longitudinal and transverse direction, but they are poor when it comes to shear. Suppose we want to enhance the shear stiffness, so we include say 45-degree layers, but as soon as we put one 45-degree layer, that immediately leads to the existence of A16, A26, which is actually 0 for 0 and 90 degree. Therefore, including a 45-degree layer will lead to shear extension coupling, but if along with that 45-degree layer there is another minus 45-degree layer, that means, if they come in pair, then this A16, A26 term could be eliminated. So, that is how a balanced laminate is important. Okay. While we provide the required shear stiffness, at the same time we could eliminate the shear extension coupling. Okay. So, also note that if we add 0 degree or 90 degree layer, these characteristics, the characteristic does not change. What is this characteristics? A16, A26 is 0. This characteristics does not change. That means, inclusion of 0 or 90 degree layer in a balanced laminate does not change its characteristics of A16, A26 0, because for 0 or 90 degree layer anyway A16 and A26 are 0. Okay. Therefore, if we say there is a balanced laminate, say plus 45, minus 45, say again say plus 45, say minus 45. Okay. This is balanced. Okay. It is not symmetric, but balanced. Okay. Then we can add 0, plus 45, minus 45, plus 45, minus 45, 90. It does not change the characteristics. For these also A16, A26 are 0. Therefore, it could also be considered to be a balanced laminate. Okay. Then balanced laminate could be symmetric also. Okay. Say plus minus 45 symmetric is a symmetric balanced laminate. Okay. What is the characteristics? Because it is symmetric, B is equal to 0. In addition, A16, A26 is equal to 0. Okay. So, this is about symmetric laminate. Now, if a laminate does not have symmetry, okay, if a laminate does not have symmetry, then it could be unsymmetric laminate, or also called asymmetric, or non-symmetric, whatever, I mean same thing, it does not have symmetric. Okay. So, what is the characteristics of unsymmetric laminate? That means, in ABBD matrix all the matrices are there. That means, with respect to a symmetric laminate, in an unsymmetric laminate B is not equal to 0. That means, bending, extension, coupling exist. could also be anti-symmetric laminate. Anti-symmetric laminate. Okay. What is an anti-symmetric laminate? An anti-symmetric laminate is where the balanced pair of theta and minus theta, where this is also a balanced laminate, but balanced pair of plus theta and minus theta are symmetrically placed, are symmetrically placed with reference to the mid surface. That means, suppose you have a laminate and for this is the mid surface or the reference plane, say there is a layer at a distance of z k bar for which the fiber orientation is theta k and its thickness is t k. Then there is a layer which is below this mid surface at the same distance, say this is z k prime bar, but this is minus. So, theta k prime is equal to minus theta k and its thickness is same. So, this is antisymmetric. Okay. T k is equal to T k prime, theta k is equal to minus theta k prime and z k bar is equal to minus z k prime bar. Okay. So, this is an antisymmetric. That means, for each plus theta layer there is a minus theta layer of identical thickness and same material, but having and they are placed symmetrically with respect to the middle surface. This is called antisymmetric laminate. Now, this antisymmetric laminate definitely it is a balanced. So, because it is balanced, because it is since it is balanced, therefore, we have already seen the characteristics of balanced laminate is A16 is equal to 0, A26 equal to 0. Okay. In additionally for antisymmetric laminate, D16 is equal to, by definition of D16, k is equal to 1 to n Q16 bar k z k cube minus z k minus 1 cube is also equal to 0, and similarly D26 is also equal to 0. Why? You know, because for each Q16 bar k there is, because it is for theta, there is a Q16 bar k prime is negative, because Q16 since Q16 theta is equal to minus Q16 minus theta. So, by the same logic T26 is also 0. Therefore, the characteristics of an antisymmetric laminate is that the characteristics of an antisymmetric laminate is that A16, A26 are 0, additionally D16, D26 is also equal to 0. However, because it is not symmetric, therefore, the bending extension coupling exists and B is not equal to 0. Okay. Similarly, there could be antisymmetric cross-ply laminate. Anti-symmetric cross-ply laminate. Like symmetric cross ply, here also each ply is a specially orthotropic plies, but for a 0 degree above the mid surface there is 90 degree. Okay. Say this is 0, 90, 0, 90. So, this is an antisymmetric cross ply laminate. Okay. Like for antisymmetric angle ply, for each plus theta there is a symmetrically placed minus theta. Here for an antisymmetric cross ply laminate, for each 0 degree there is a symmetrically placed 90 degree layer made of the same material. That is why it is called antisymmetric cross ply. 0, 90, 0, 90 is an antisymmetric cross ply laminate. Okay. So, because it is all the layers are actually because all the layers are made of specially orthotropic, therefore, A16, A26 is equal to 0, and D16, D26 is also equal to 0, and of course, because it is not symmetric, therefore, B is not equal to 0. So, this is antisymmetric cross ply laminate. Okay. There is another special class of laminate which is called quasi-isotropic laminate. Quasi-isotropic laminate. What is a quasi-isotropic laminate? Quasi-isotropic means it is isotropic in some sense, it is not fully isotropic. Okay. Therefore, a quasi-isotropic laminate is a laminate which shows isotropic behavior, under in plane loading, that is why it is quasi-isotropic, not in bending. Okay. And is defined as a n layer laminate, and n such that n is at least 3, number of layers should be at least 3, n layer laminate such that n is greater than 3, greater than or equal to 3. It is an n layer laminate where the fiber orientation, of the adjacent orientation of the adjacent layer or lamina is incremented by pi by n. What does it mean? Suppose we have a 3 layer laminate, lamina laminate, then what will be the stacking sequence? Okay. If first is 0, next is pi by n, that means it should be 60, pi by 3, then next will be again incremented by 60, that means 120. Suppose it is a 4 layer laminate, n is equal to 4, then tell me what will be the angles if we start with 0, first is 0, then pi by 4, that means 45 degree, increment the next by 45 degree, that means 90 degree, increment the fourth layer again by 45 degree, that means 135 degree. So, these are quasi-isotropic laminates. Similarly, you can have n is equal to 5 also, and you can keep on increasing that. Only thing, the increment in the fiber orientation angle will be by pi by n. Okay. For a 3 layer laminate, how it looks like? First layer is 0 degree. Okay. Second layer is 60 degree, third layer is 120 degree, 0, 60, 120. These angles are with reference to the laminate xy. Okay. The fiber orientations are with reference to that laminate axis xy, and now you can clearly see this 120 is nothing but with respect to xy it is minus 60. Okay. So, this could be written as 0, 60, minus 60. Similarly, the 4 layer laminate, first one is 0, second one is 45, okay. Third one is 90 and fourth one is 135, 0, 45 with respect to x y, 90, 135. You can clearly see this 135 is nothing but minus 45. Okay. So, this could be written as 0, 45, 90, minus 45. These are quasi-isotropic laminates. So, what happens if it is a quasi-isotropic laminate? For this type of laminate, it could be shown that the A matrix for this kind of quasi-isotropic laminates, the A matrix becomes this leads to A matrix becomes A11, A12, 0 and A22 is equal to A11, A26 is 0 and A66 is A11 minus A12 divided by 2. So, this it could be proved that for this kind of quasi-isotropic laminate the A matrix takes this form. That means, A11 is equal to A22, okay. A16, A26 is equal to 0, A66 is not independent, it could be expressed in terms of A11 and A12. So, this A matrix is like a, we are all conversant with isotropic materials where there are only two independent. Okay. Here also it is only A11 and A12 and other two are same. Therefore, what is A11 is equal to A22 means in both the x and y directions the stiffness is same for the laminate, okay, in the under in plane loading. Please note that A represents in plane loading. Therefore, this A matrix which is the representative of the in plane response of the laminate. So, this A matrix is actually it behaves like an isotropic material. Therefore, this laminate is called a quasi-isotropic laminate. That means, it behaves like an isotropic material under in plane loading and not under not under bending, okay, not under not in the D matrix is not isotropic, it is only A matrix. Okay. So, the in plane behavior is isotropic, therefore, it is called quasi-isotropic. Okay. Now, since it is characterized by A matrix, since it is characterized by the A matrix is the characteristics of the quasi-isotropic material, and we know A does not depend on stacking sequence. We have discussed this in details earlier. It is only decided by the number of layers and their properties and the thickness, not by how they are stacked. Therefore, if 0, 60 minus 60 is quasi-isotropic, then 0 we can write minus 60 is also quasi-isotropic. Is that clear? Going by the same logic, 0, 45, 90, minus 45 and 0 plus minus 45, 90 does not have any difference as far as the A matrix is concerned, because it does not depend upon the stacking sequence. Therefore, both are quasi-isotropic. Okay. So, we can change the stacking sequence, does not have any influence, but when you change the stacking sequence, please note that these two will have different D matrices. Okay. These two will have different G matrices. So, we can also have a symmetric laminate 0 plus minus 45, 90 symmetric. Okay. So, in this case B matrix is 0 and then A matrix behaves as an isotropic, therefore, it is a quasi-isotropic laminate. So, the characteristics of quasi-isotropic laminate is that under in plane loading, please note it is only under in plane loading it behaves isotropically, but it is only stiffness. Okay. The strengths may not be independent of direction. Okay. Now, what is the importance of this laminate? If you look at the stacking sequence of this laminate, we have 0 plus minus 45, 90, 0 and 90 as usual, you know, they provide stiffness in the longitudinal and transverse direction, and presence of plus minus 45 actually provides the shear stiffness. Therefore, we have a laminate where it has both longitudinal, transverse and shear stiffness. At the same time, under in plane it behaves isotropically. So, this is the characteristics of quasi-isotropic laminate. So, we have discussed in brief today the different types of laminate stiffnesses, because many times it is required that some of the stiffness elements, some of the elements of A, B or D are made 0 to avoid undesirable response of the laminate, and that could be done by judiciously choosing the material and the geometrical parameters, that means the stacking sequence, the thickness and the materials of each lamina. Okay, I will stop here today. Thank you.